we'll start a new chapter called Principal Component Analysis. I think it's a very common, it's a very commonly covered topic in a lot of courses in data science, big data analysis. Principal component analysis is always a widely used method. So I think in the lecture slides here, I will basically give more explanations from first we'll look at why PCA is an important technique, and I will focus on the mathematical formulation of the problem and how the constraints optimization technique can be used to solve the PCA problem, and how this technique can be applied to a famous example called eigenphases. And actually in assignments for the PCA, we will implement something that is similar to the eigenphase, but use another different data set. All right. First, let's look at what PCA is and why do we need to use such a principal component analysis technology. Okay. So to put it simple, it is a dimensionality reduction technique. Okay, and what it does is to remove the redundant or unwanted dimensions. Okay, so here the redundant and unwanted, they are very subjective and very subjective terms that's totally up to you to decide, like to the data user to decide. So if you think that these dimensions, they don't carry very important information, then you can think of it to be redundant. Okay, there's no objective standards for deciding which ones need to be kept, need to be removed. So, but PCA provides provides a quantitative method, a quantitative way to help decide which dimensions they carry more information. Okay, so it basically is a way to distill or to make life easier. Like we can remove the redundancy in the data so that the data analysis process can be easier to conduct. Like we are not overwhelmed by too much dimensions, too much information. So, for example, such a technique, dimension reduction technique, can be applied to the word embeddings we just covered, right, in a previous lecture. The word embeddings, they are very high dimensional data sets. Like at least it will be having 100 dimensions, and all these dimensions, they don't have explicit meanings. And sometimes it just don't, it's just the case that all the dimensions matters. Right? There's always some dimensions that don't carry too much information. And it's even more true when the image, so when you have more dimension data sets, right? You have image, you have 64 by 64 pixels, then of course, if you keep all the information, that's too dense, and that's not all dimensions are necessary. So we'll use a simple example to motivate PCA here. The first example we look at is from the bird data sets. And each column is a data instance here, and we have each row as our feature. So it may be our traditional way, conventional way, is to flip around, is to transpose the table, right? Each row should be an instance, but it's okay. It's just a transpose of our conventional view. So we have shown weight, wingspan, and the length of a bird here. And given a bunch of bird data points, several questions can easily arise, like how we visualize data and which features are correlated, right? We have weight and length. So intuitively speaking, if the bird is longer, then it tends to have a larger wingspan, right? And also it tends to be heavier in weight. So these features shown here, they kind of have the collinearity issue. They are not totally dependent features. So that makes it more complicated because we need to choose the features to describe the data, to represent a word, to represent a bird. Like if we want to plot all the data points, which two dimensions do we need to choose so that the visualization is most expressive, right? Another example here, we have the student data, right? We have the weights, the heights, maybe the historical SAT scores, IQ scores. But given these features, we still have the same problem. Which features do we need to use to describe the students so that the most informative patterns can be captured, the most useful information can be used to describe the students, right? To describe a person. So given just similar to the first data set here, the same question arises, like what features do we need to use so that the collinearity issues are kind of considered. All right, so let's think about the question of what a good feature is, or what good dimensions are need to be kept. So we assume that good dimensions, those dimensions that give higher resolution, which means the data points along that dimension should spread out as much as possible. They should not cluster into one point, right? If we choose a dimension and if we observe the data along that dimension, all the data points collapse together, then there's no information at all, right? And also we want the dimensions to be independent. So we want to avoid redundancy. So if I use if I want to model the housing price, like the price of a house may depend on the area, like square feet, but also in number of bedrooms. But these two features are kind of correlated, right? So we want the features or the dimensions selected to have less interdependency. So this is what exactly TCA does. It will find you a new set of dimensions, and such that all the dimensions are orthogonal, which means they are independent. They are totally independent. And also, these selected dimensions are ranked according to the variance of data along them. Okay, we have a mathematically defined measure of variance of data along each dimension. Okay, so because we want to rank the dimensions so that the highest ranked dimensions have the largest variance of data, because large variance means that the data are spread out. So think of the standard deviations among data sets. So among data points, if you have large standard deviations, which means your data is spread out a lot, which means you can observe the data clearly. If the standard deviations are very small, which means that dimension doesn't contain any information, doesn't contain useful information. All right, so let's start this simple example here. We want to reduce, this is a simplified version of the birds example, right? We only keep the 2 dimensions, the weight and the wingspan, and also we have 6 birds in the data points. So now we already have 2 features, and maybe our task is to select the to reduce from the 2D space to 1D, which means we only want 1 dimension to be kept. Okay, and let's see how this procedure looks like. Although in practice we don't need to, we usually don't need to reduce under 2 dimensions. We just usually the target, the goal is to reduce from a higher dimension space to a 2D space. But here, in order to give a illustration of how the procedure goes, we use example of reducing from 2D to 1D. All right. So given these 2 features, one thing we need to first compute is the means and the variance for each dimension, which each original dimension, which is feet weight. So the mean weight is this 5.833, and the variance across all the weights is 4.355. And for the wingspan, we compute the mean and the sigma, which is the standard deviations. Okay. So if we plot the data points, it will be like this. Okay. And remember that, notice that here, this is not the 0 points, right? With all these values, they start from non-zero points. All right, so the next thing we want to do is to normalize the data, right? Which is a typical operation by subtracting the mean values from each data points and divided by the standard deviations for each feature. So for the, let me use the color, correct color. So for the weights, we need to use the mean of weights to subtract from each data points and divided by the standard deviation of weights. And for wingspan, we will need to do the same thing. We need to use the mean of wingspan to subtract from each data points and divided by the standard deviation. So this will give us a normalized data points, and we call it tilde. So we have this little curly wave above the x1 and x2. So these are already normalized. So one characteristic of this normalized data is that it centers around the 0 points, right? Because we subtract all the mean values from each data points. So if we sum up all the data points, all the normalized data points, the score will have 0 points as a result, right? And also the divided by the sigmoid, the divided by the sigma, divided by the standard deviations also means the variance, they are at the same scale along each directions. All right, so we have a very beautifully normalized data points, looks like this. So our goal is to find a dimension that best describe the data. Remember, our goal is to find the dimension that will will keep the highest amount of variance among data points. Okay. We want to characterize as much variance as possible, and also that means we want the data points to spread along that dimension as much as possible. Okay. So basically the task is to find a good dimension to project, okay, to project the data points onto. For example, if we consider this blue dashed line as the candidate dimension, then what would happen if we project the data points onto these candidates? So we can compute the total variance along this dimension by projecting all the data points to the candidate dimension. For example, the point P1, if I project it onto the dimension here, it will result in a new point here, and there's a distance from this projected location to the 0 point. And this distance d1 is called the distance of the projection. Okay, and this d1 will be used to measure the total amount of variance later. So for P2, we also have a distance d2. And for all the data points, we would have a d associated. So we can use the sum of squares for all the d's to indicate the total amount of variance after we projecting all the data points onto the candidate dimension, right? Because we have 6 data points, then the summation of the di square is the total amount, sum of squares, is a total amount of variance, okay? So we want to maximize it, because if we select a different angle, if we choose different angle, all these data points, they may cluster, they may collapse into a very narrow range, and that is not unwanted. All right, so the problem becomes to maximize the sum of the squares of the projections. Okay, so this is the first candidate we considered. What if we like turn over the candidates a bit clockwise? Then it will show us a different projection, right? If we further spin around, it will give a different projection. Okay, so maybe until some points indicated by this red dashed line, it could be an ideal dimension that we want to use to project all the data points, because this direction maximize the sum of squares, right? And we will call this principal, this is the principal components, or PC1, the first principal components, PC1 here. And this PC1, if we conduct the projection onto the PC1, then we will find that the sum of squares is maximized. Okay, and we can indicate, or we can represent the PC1 using a unit vector. Okay, the unit vector is described by these 2 numbers. It basically points to the direction of this dimension. Okay, and the new dimension here is the linear combination of the original 2 direct dimensions, x1 tilde and x tilde. And this u1 is a linear combination of both, which is 94.94 times the x1 tilde plus 0.34 times the x2 tilde. So this is the meanings of the coefficients of the 2 of the unit vector of the principal components. Okay, and similarly we will have the second principal second principal components by looking at the direction that's perpendicular to the PC1. Okay, so the PC1 the PC2's direction, the second principal component's direction, is actually perpendicular to PC1, which is indicated by this red arrow. And it can also be represented by 2 numbers. But as you can examine yourself, if we compute a dot product between these U2 with the U1, you will have 0. Okay, because these 2 are perpendicular. And we call the PC2 the second principal component, because the projection onto the PC2 is much smaller than PC1. So if you compute, if you look at the projection onto the green dimension, then the total summation of variance is much smaller than the projection onto the red one. So now, given the PC1 and PC2, we can use PC1 and PC2 as our new dimensions, and we can rotate it the original data points onto the directions of PC1 and PC2. So these will represent the data with larger variance. So because the PC1 explains more variance than the original weights, original feature or original dimension weights. And if you look at the projections of the data points onto weights, it can explain the data points in terms of SS, that many of variance. But if you compute the projection onto the PC1, the variance SS prime is much bigger, than the than using the original feature. Okay, because PC1 is a linear combination between weights and the wingspan, and so the total summation sum of squares here includes some parts of the variance along weights and also some parts along the variance of wingspan. So you can think of that PC1 is a newly constructed feature other than weight and wingspan. The PC1 is different from wingspan and or weight, but it's a kind of a combined feature, a new feature that represents the data points. Okay. So yeah, that is basically the results we want to achieve using principal component analysis. And I think I will cover this slide and leave the rest parts of the results to the next lecture. So of course, we care about how do we compute the principal components. Given the data set, how do we find the direction that a dimension that maximizes the sum of squares, right? That is the key questions that we care about. So the goal is to determine the principal components. And we know that a principal component is a unit length vector. In this example, it's a 2D space. It's a two-dimensional vector, U1, U2, right? So also, given a data points, the i's data points, x1 tilde I and the x2 tilde I, we can compute the length of projection for that data points along the PC1, along the PC, right? We just need to compute the inner product or the dot product between two vectors, right? This will help us to compute the length of the projection. So the sum of the squares of the projections is described by this equation. We just need to sum up the squares of all the projections across all data points, right? If we expand this inner product term, it will give us such an expansion, right? And if we further look at if we represent this with a matrix notation, because we listed all the data points by columns, right? The first data point is this x1, x2, and second is also x1, x2, but with these superscripts in the brackets. So given this matrix representation of the x tilde, we can represent the sum of squares with this matrix formation, matrix multiplication form, which is x tilde times x tilde transposed, right? If you think of x tilde transpose, it's just a two-column matrix, right? And you times x tilde with x transpose and times u transpose and u, one on the left and one on the right, you will have exactly what's expressed here. So this is the matrix expression of the sum of squares. And our goal is to maximize this SS. We want to maximize this quantity. And this 1/m is just for normalization, okay? It's just for the ease of computation in the later steps. And this is the problem we want to solve. It's a optimization problem under these constraints, because we said that the principal component is a unit length vector, right? This constraint must be here, because otherwise there are infinite possible representations for the vector, right? We want to constrain that the length is unit length. Okay, so it becomes a very similar problem that we have come across in the when we introduce support vector machines. It's a constraint optimization problem, right? Our constraint is a equation here, and our goal function is basically a quadratic function, right? So we can use the Lagrangian multiplier to solve this constraint optimization problem. So we will use I will leave the remaining part to next lecture, and we will see how the PCAs can be solved by conducting Lagrangian optimization techniques. And that's pretty much of it today. And thank you for coming. I will double check the assignments A to see if there's a problem in there.